A transistor. 3 nanometers. The foundation of every computer ever made. That foundation has now shrunk to just 10 atoms wide. There is nowhere smaller to go. And so we are forced to abandon the classical bit, a simple 1 or 0, and turn to a qubit, which can be both simultaneously. Because classical computing tries solutions one by one, but quantum computing explores all of them at once. To build a machine that does this, you first need to build the coldest machine on Earth. The first cooling stage takes us to 70 Kelvin colder than liquid nitrogen. Descending further, at 4 Kelvin helium liquefies, and key components become superconducting zero electrical resistance. But we must go colder still, down to 15 millikelvin, just 15 thousandths of a degree above absolute zero. Only at this temperature does the quantum chip sit superconducting and ready for operation. Because thermal noise kills quantum states in picoseconds, this extreme cold buys us milliseconds instead. The result is a quantum chip 180 times colder than the void of deep space. With the chip frozen, we control it using microwave pulses sent from room temperature down into the cold. And all of this, the massive cooling, the shielding exists for one reason, to keep that tiny chip at 15 millikelvin. On that chip, a junction looks simple, but what it does is not simple at all. Inside that junction, Cooper pairs of electrons quantum tunnel through a barrier they classically cannot cross. This makes the superconducting qubit an artificial atom built by us, not given by nature. The most robust artificial atom we've built is the transmon qubit, the workhorse of today's quantum processors. Just 127 transmons can represent more possible states than there are atoms in the observable universe. Because, in superposition, a qubit is neither 0 nor 1, it is genuinely both at the same time. So 2 qubits process 4 states at once, 10 qubits process 1,000 all simultaneously. But superposition alone isn't enough. The deeper power is entanglement, 2 qubits sharing a single quantum reality. Measure one entangled qubit, and the other responds instantaneously, no matter how far apart they are. We manipulate these entangled states using quantum gates operations that rotate a qubit state on a sphere called the block sphere. This unlocks algorithms like Grover's, which searches unsorted databases quadratically faster than any classical computer ever could. Or Shor's algorithm, which factors large numbers in hours, a task that would take classical machines millions of years, breaking today's encryption. That looming threat has already spurred a response, post-quantum cryptography, based on math problems even quantum computers can't efficiently crack. But all these algorithms fight a common enemy, decoherence, the qubit losing its delicate quantum state to environmental noise. Today, we get about a millisecond, roughly 50,000 gate operations, before decoherence destroys the computation. To fight back, we use surface code error correction, which detects errors and corrects them before they can spread. But this protection is expensive. It takes roughly 1,000 physical qubits to build just one stable, error-free logical qubit. Once we have logical qubits, a quantum algorithm can sculpt probability, making the correct answer emerge inevitably at measurement. That opens the door to simulating molecules with exact quantum mechanical accuracy, something no classical computer can do. One such simulation of the nitrogenase enzyme could unlock a room temperature way to make fertilizer, changing global energy forever. Beyond simulation, quantum optimization tackles fiendish combinatorial problems like routing and logistics far faster than before. And yet, the biggest application of quantum computing hasn't even been discovered yet. So where are we now? In 2026, quantum computers are real, but they are still not fault-tolerant. $50 billion invested globally, 4 competing hardware approaches racing toward one transformative prize. Fault-tolerant quantum computing is projected by 2030. The physics leaves no doubt it is possible. Even today, this refrigerator-sized machine can, on specific problems, outperform every classical supercomputer combined. The impact will cascade, chemistry changes first, then optimization, then cryptography, then everything. After all, nature itself has been quantum computing for billions of years. We are just now catching up. So this chip, which looks ordinary, computes in a state space larger than the entire universe. The goal, 1 million physical qubits, yielding 1,000 logical ones, the true fault-tolerant quantum computing era. And that one machine will transform at least 6 major industries from energy to medicine. The transistor sparked the first computing revolution. The qubit is now igniting the second. So what would you use a quantum computer for? Drop your answer below. The transistor changed the world, and most didn't see it coming. This moment looks exactly the same. We are no longer just computing, we are building machines that compute in the way the universe itself computes. If that vision excites you, subscribe to NexaVision. If this shifted your perspective, hit the like button, it helps more than you know. Next on NexaVision, the room temperature superconductor, the material that rewrites energy. Thank you for going inside a quantum computer.